Yes, we are live now.
Okay. So you start.
Yes.
Okay. Good morning, everyone. Welcome to the IWYM talk series. I'm Manish. I'm a consultant with IWMI working on forest hydrology, eco hydrology, springs, streams, etc., and still very much a PhD student at A3. It is my great pleasure to have Dr. Sally Thompson with us, who is an associate professor, lead of surface and eco hydrology research group at the School of Civil, Environmental and Mining Engineering at the University of Western Australia. She is also, I have been told, a transcontinental advisor who has students in US and Australia, and a very, very supportive PhD advisor. She's also very active on Twitter, and she's here to talk about how to make errors and not be too serious about hydrological models. Welcome, Dr. Sally.
Thank you, Manish, and hi, everybody. I'm so pleased to be able to join you today. I thought I'd start this talk with a little bit of intercultural exchange and introduce you to the muddle-headed wombat, who is a much-loved character from Australian children's fiction, and he might be our spirit animal for this particular talk. Now, the reason that I wanted to talk about the ways that we can make errors in hydrology are that there are many traps that the study of the water cycle can present us. And I think particularly when we're getting started and haven't fallen into those traps, we may not recognise that they are there. So some of these traps, I think, are fairly obvious, or certainly once we talk about them, we'll think, oh, yes, that is obvious. Some are, I think, less obvious. And the risk with falling into a trap and becoming muddled, I apologise, goodness me, models and muddles, becoming muddled about our hydrology is that we may make decisions that are based on a false premise. And that can undermine our credibility. It can send the scientific discipline off in a bad direction. And it can also, when we're working in a more applied or management context, lead to terrible wasting of precious resources if we, for instance, start trying to solve a problem in a way that actually isn't connected to what's causing the problem. So we want to think about these traps, and we'd like not to fall into them. So the way that I've structured this talk is to list 5 really great ways to make hydrological mistakes, and to try to illustrate these with examples from my group's research history. And because I'm not quite shameless enough to share all the errors that we really did make, a lot of the time I'm going to illustrate these errors or these traps as ones that we could have fallen into and were lucky not to. So this isn't just a story of all the times I got things wrong. Mostly, hopefully, it's a story of the time we got things right, but where we were lucky to get them right in some respects. Now, I don't want to just give you a list of ways to do things wrong. I also want to think about how we can protect ourselves from making these errors. And so I'll finish up the talk with some thoughts about ways that we can avoid falling into these traps. So, without any further ado, I'd like to get started on my list of 5 fantastic hydrological errors to make. Here's error number 1. Don't question the gurus. Now, before anybody starts to worry that I'm being terribly offensive towards somebody's spiritual leader, the man on this slide is not any kind of spiritual guru, but a popular host of an Australian gardening show. But I think he looks the part. The gurus that I'm talking about, of course, aren't really spiritual or religious gurus either, but the wise men and women who think that they know what is going on in the water system that you are trying to study. And you will probably encounter these people all the time in your career, particularly if you're a young researcher. Here in Western Australia, the favourite thing for these people to say is, why are you bothering to do that? We did it all in the 1980s. And you think, did you really? Is that really true? And these are also the people who will tell you with great confidence, here is what is going on in this system. I already know, we don't need to do any more research. Now, you should certainly talk to the gurus, and the gurus might be right, but you should not fall into the trap of failing to question the gurus. And to illustrate why this can be such a trap, I wanted to share some of the research that our group had done in collaboration with A-Tree around the processes going on in the Arkavati Basin near Bangalore. And for those who are not based in the Bangalore area, the Arkavati River Basin flows to the west of the metropolitan part of Bangalore and is a tributary to the Calvary River. And just west of Bangalore, it is dammed in a large reservoir known as T.G. Hully Reservoir. Before about the 1970s, this reservoir was a major drinking water supply to the city of Bangalore, but it has become less and less viable and less important as a water source since then because the inflows to the dam have been declining. Now, in about 2013, so a little while ago now, we started to work with researchers at A-Tree to try to put together the story of why the Arkavati River was drying. And of course, as part of doing this, we talked to a lot of gurus, and everybody had opinions. The water managers had their say. The catchment restoration groups had their opinions. The academics had opinions. The farmers had opinions. Most of the time, the opinions didn't wholly agree with each other. And so these were some of the things that the gurus told us. The river is drying up because it is raining less. This was quite popular with farmers. The river is drying up because the climate is warmer and there is now more evaporation, and so more water is going into the sky, less is going into the river. This one was quite popular with the bureaucrats. We've had a big expansion in eucalyptus plantation area. That's a very thirsty crop. This is doing more evaporation. That's why we don't have a river anymore. And, you know, this is feasible in some ways. This is a lovely, well, I don't know how lovely it is, but it's a cool image. It's from a borehole about 30 metres below the land surface, and you can clearly see eucalyptus roots getting down that deep. So they are certainly very good at getting water out of the soil profile. But there were still more reasons. Actually, according to some people, the river is not flowing because there are so many check dams being constructed and so much sand mining excavating the river channel. And together, this means that the river just can't flow from its headwaters to the dams anymore. It's getting stuck and turned into a bunch of lakes. What none of the gurus, as far as I can recall, ever said to us was you should take a look at groundwater extraction. But knowing that there had been big changes in groundwater irrigation for agriculture, we put that one firmly on our list. So I hope it's already apparent that there's a trap here, that if you listen to one of these gurus alone, you wouldn't have this range of explanations to think about, and that it was really important here that we question what we were being told and see if we could evaluate evidence to push us in the right direction. So let's have a look at some of the evidence. Here we have a plot of the inflows to the T.G. Hully Reservoir from the period of about 1940 to 2010. And sorry, the year scale is right at the bottom of the slide there. What we can see is that if we look at the period of 1938 to 1975 as a baseline, that over the next 25 years, the median flow halves. And then from the year 2000 onwards, the median flow halves again, so that we've lost something around 75% of the flow in this river basin. So yes, there's a problem. But when we start to look at the rainfall time series, we certainly see lots of fluctuations, but we don't see that same trend of halving and halving again when we look at these median rainfall values. And in fact, the median rainfall values in that 2000 to 2010 period are really comparable to what they were in the much earlier period of time. So is it raining less? Well, there's drought years and there's non-drought years, but over many years, no, it's not raining less. Could it be that this evaporation hypothesis is correct? Now, this is challenging to evaluate because there aren't long-term measurements of evaporation in the basin, but there are long-term temperature measurements which can be used to make a reasonable proxy for evaporation, or at least for potential evaporation. And you would think that these would be responsive to anything that was going on with global warming. And again, we see the same sort of pattern, that there's interannual fluctuation, although not really too much, and not really a big increase in how much evaporation could happen due to changes in climate. The one thing that we did see some clear trends in, other than the inflows themselves, was how much of that inflow was driven by base flow. So that is how much of the inflow was happening in months when there wasn't any rainfall, and that's what those blue bars show. And then in a later period of time where we had more highly resolved data, so we had daily flow data, then we were able to calculate a base flow index, a proportion of the annual flow that was coming from base flow. And by both of those measures, what we're seeing is less and less base flow over time. So that starts to look a little bit suggestive. So at this point, we can start to do things like say, well, maybe the rainfall, maybe the evaporation hypothesis doesn't seem so plausible. Can we look at other sources of information to try to find out what might be going on in this basin? And what we decided to do was to use satellite records and to look at the irrigation tanks left over from the historic cascading tank irrigation system in the Arkavati Basin. Now, there's thousands of these tanks and hundreds of them that were large enough that we could map the area of surface water in them using the Landsat satellite product. And in doing that, we were then able to start making maps of what was the trend in the surface area of the water in these tanks. And that's what I'm showing you in this figure. So we've divided up the Arkavati River Basin into a number of sub-basins containing multiple tanks, and we do it in this kind of coarse way just so that we have a little bit more statistical power. Then we've asked what is the trend in the surface area of water in these tanks. Now, if that trend is statistically significant, that is different from zero, then the sub-basin has been outlined in black, and then the colour of the basin indicates the strength of that trend. Where it's blue, we're actually seeing expansion of the water area, and you'll notice that those blue watersheds are clustered downstream of where the Bangalore city limits are. So this is almost certainly urban wastewater discharges, and those of you who are familiar with the area will have seen some really lovely black water streams in those watersheds. But the areas coloured in red are places where there was less and less observable surface water over time. And since these tanks fill up along the river network, if they're not expanding and filling in the wet season, it's an indicator that there's not actually stream flow happening where those tanks are located. So this very negative trend gives us a good indication of where we're losing flow in the basin. What we were then able to do was to correlate these trends with the land use in the basin. And what really shows up is that it's irrigated agriculture that is most closely associated with these big declines in stream flow. So what have we learned from this? Well, we've learned some nice things about the Arkavati, but for me, one of the big take-homes is really this don't question the gurus as a trap, because none of the gurus mentioned groundwater as an issue, and yet of all of the explanations that seems to stack up for why this river flows decline so much, groundwater seems to have the strongest effect. Now, certainly eucalyptus plantations are part of the story, certainly modifications to the channel are part of the story, but we are reasonably confident that groundwater is the really big part of the story here. So watch out if you're not questioning your gurus. I want to continue with the story of the Arkavati River a little bit, because saying there's an association between an expansion of groundwater irrigation and a loss of surface water resources is a nice observation, but it doesn't really get us down to why those two things should be connected at all. And if we want to start thinking about solving problems, we'd really like to understand the why of it. So in continuing to think about the Arkavati, I have two more traps for you. The first one you can fall into is to completely ignore runoff generation mechanisms. Who cares about them, right? And in a related fashion, confine yourself to a single method of investigation. What I hope I can illustrate now is that in trying to further solve the mystery of what was going on in the Arkavati, these traps would have really gotten in our way. And so I want to start by reminding everybody about runoff generation mechanisms. We're trying to answer the question of why it is that increasing groundwater abstraction might result in less flow in the rivers. And we thought that the route to understanding this had to go on a path of first understanding how it is that water gets into the river system today, and then asking whether there were other ways that it could have gotten into the river system in the past, or whether something had changed that meant that we were just getting less of today's processes happening. So to do this, we had to look at the runoff generation mechanisms. Now, broadly, we think about water rainfall getting into a channel either through overland flow paths or through the groundwater. And that groundwater discharge could be the fairly slow discharge of a regional water table that's intersecting the stream, or the much faster process when a perched water table forms during a storm and discharges into the stream only while the storm is going on and shortly afterwards. When we think about the processes where water is getting into the stream by moving over the land surface, that can also happen in several ways. That can be because the rainfall is coming in faster than the soil can infiltrate it, and so the difference between the two collects and forms runoff, and we call that infiltration excess. But it can also happen when the soil profile is full up with water and can't take any more in, and in that case rainfall will also not be able to enter the soil and will form runoff, and we call that saturation excess. So how can we go out to a watershed and work out which of these things is happening? Well, we can start to find out whether or not overland flow is occurring through the fairly simple approach of standing in the watershed during a storm and having a really good look around. Knowing that we can't always have people there, we can also deploy flow traps on the land surface that will collect any water that is flowing laterally. We can also ask whether infiltration excess is a possible generating mechanism by comparing the rate of infiltration that can take place in the soil with how rapidly the rainfall's coming in. So now we need to get people in the field, we need to put out flow traps, we need to measure rainfall at fairly high resolution, and we need to make measurements of the soil hydraulic properties. If we want to differentiate saturation excess from the infiltration excess, we also need to know whether or not the soils are saturated. So now we need to have a look at what the soil moisture dynamics are and how they relate to the production of runoff, which we can measure with flow in a channel or by the inflows into a local tank. We can also start looking at differentiating the saturation excess and the groundwater discharge from infiltration excess by considering whether or not there's any signal of old water in the runoff. And by old water, I mean the water that was already sitting there in the soil or the groundwater before the storm came in. And if we're going to do this, we need traces that can give us the difference in the chemical properties of the old water and the new rainfall. And then we also need to have a look at whether there even is a water table present, which we can do by looking at wells, looking at bores, and also by looking at the soil moisture. So I hope even this little schematic starts to give you a sense that if we want to look at different runoff generation mechanisms and work out what's going on, that we need to start looking at quite a broad range of different techniques to learn about our system. So I'll show you some of what we found when we put these techniques to work into milli watersheds in the Arcavity Basin. The traces are the first thing I'm going to show you, and the traces we used were isotopic traces, and specifically the concentration of deuterium, so heavy hydrogen, in water. Now, what tends to happen is that water that's hanging around in a catchment will evaporate, and this concentrates the heavy isotopes in the water that's left behind, so that old water looks quite different to new water when we compare the concentrations of this tracer. So we took measurements throughout the course of several storms, and I'll show you data for two of them, Storm A and Storm B. Storm A is coloured in red here, Storm B is coloured in blue, and we made measurements in the precipitation, so that's given by the upright cross, in the soil water, which is given by the little X, and in the runoff, which is given by Q. And if we focus on Storm A, what we can see is that the isotopes in the runoff look a lot like the isotopes in the rain. They're really similar to each other. These circles and crosses are pretty much lining up with each other. Storm B looks different to Storm A. That's pretty usual. But again, what we're seeing is that the runoff is pretty similar to the rain. And for both storms, if we look at the water in the soil, it's quite different in its isotopic composition to the water that appears in runoff. And so this is starting to give us an indicator that what's showing up in the stream is the rain that just fell, and that rain is not pushing water out of the soil, it's not pushing water out of the groundwater, it's really just the immediate rainfall. There's no signal of old water in the runoff. Well, we can look at some of the other things we did. We have some infiltration experiments. We did more than 30 experiments with an infiltrometer, which I'll tell you on the clay soils there is a big ask, and hats off to the field crew who did that. And what this lets us do is make estimates of the hydraulic conductivity of the soils. Those are shown in the second of the plots here, the box and arrow plots, as a function of the land cover, so that we generally had higher infiltration rates in the crops than under eucalyptus, but they were all, reasonably high infiltration rates. What we can do is then start to compare those to the observations we made of rainfall. So for example, we can say about 1/4 of our storms had a rainfall rate that was equal to or greater than 2 centimetres an hour. And if we trace that down, that's our purple line, we can see that already those storms would be coming in too rapidly for infiltration under most of our eucalyptus sites to keep up. And that if we sort of look at the next category of intensity, so now these are storms that occur about 12% of the time, that these guys certainly are going to generate runoff where there's eucalyptus and are going to generate runoff on more than 50% of the croplands. We can then use maps of the land cover to say what fraction of the total area in these milli watersheds is going to be producing runoff as a function of how fast the rain is coming in and how much of the time. And what this really tells us is that across the wet season, when we made the measurements, about 1 in 4 storms was intense enough to produce a lot of infiltration excess runoff over these milli watersheds. So, okay, we can kind of rule in infiltration excess runoff mechanisms as something that's contributing to stream flow, but have we really ruled out things like saturation excess? To do that, what we wanted to do was make measurements of the soil moisture in different areas. And I'm going to explain this plot because it's a terribly complicated plot. What you can see in the upper panel are data coming from 4 different sites, 2 under rain-fed crops, 2 under irrigated grapes. And for each site, measurements have been made at 2 different depths in the soil. Now, I'm not plotting how wet the soil was here at all, but what I'm plotting is a measure of when things happen in time, and specifically of the difference in the timing between when we saw the biggest generation of runoff into the downstream tank, so when most of the flow was being produced, and when we saw the wettest soil conditions at our sites. And what you can really clearly see, I hope, in this figure is that almost all of our data, almost all of the storms we measured, falls on the right-hand side of a lag of 0. And what that means is that the time when the soil is wettest persistently occurred after the time when we saw most of the runoff being formed. And that really is not consistent with a saturation excess runoff generation mechanism, because that would require us to wet up the soil in order to produce the runoff. So these things are happening in the wrong order for saturation excess to matter. The final thing we did was a well survey, and at the end of the wet season, we surveyed the really unsatisfying number of 99 wells in these milli watersheds. Every single one of these wells was dry, so we didn't see any evidence of a shallow water table at the end of the wet season. What we also did was start measuring the differences in the elevation of the local stream and the top and the bottom of the well. And in doing so, what we found was that for the majority of wells, their bottom was higher than the local elevation of the stream bed. And what that means was that if the water table had ever been high enough to have water in these wells, then there would have been the potential for a gradient to have water flow from the water table into the stream bed. So our presumption, looking at these phenomenally constructed wells, I think they're actually really exquisite pieces of engineering, but jeepers, they're a lot of work to build, right? So you wouldn't dig this thing and build this thing unless there was water there. Our assumption is that the existence of these wells gives us a measure of where the water table used to be, and that we can treat their bottoms as a conservative estimate of a historical water table height. So historically, we would infer that the groundwater levels were at greater elevation than the streams. So what does this tell us about what's going on in these watersheds? Well, we think that from a contemporary perspective, what's going on right now is that the groundwater is nowhere near the streams, so we can't have groundwater discharging into them. We don't have any evidence that the soil profile is becoming saturated or that there's a perched water table forming. So we don't think there's any saturation excess or any subsurface storm flow happening in the shallow soils. And what we do seem to have evidence for is infiltration excess runoff. Looking back in time, we can start to reconstruct past situations by thinking about how that infiltration capacity might have changed with land use, but also by looking at these well surveys. And pulling it all together, what we think we see is that the water table has dropped right away. This means that we can't have groundwater contributions to the channel. It reduces the likelihood that we're going to have any kind of saturation of the soil profile, because we've actually got this very deep, dry soil layer now. And so we've lost some of the pathways by which the Arcavity River's headwaters used to fill up with water. We've created all of this storage in the soil, which now is what gets filled up instead. So again, I don't think we fell into any particular traps here, but I don't think we would have been able to tell this story of why it is that the drop in groundwater would have this effect on the surface flows without interrogating the runoff generation mechanisms. And we would not have been able to interrogate these runoff generation mechanisms convincingly without using a really broad range of techniques. So ignoring runoff generation mechanisms or confining yourself to a single toolkit, I think, would be really bad traps to fall into when trying to understand these kinds of changing systems. For my last two traps for causing hydrological muddles, I'm going to leave the Arcavity system behind and take a turn off to Brazil at this point in time. And my fourth trap is to believe that all globally available data sets are going to be equally good and useful for your problem. Now, I think this is a very contemporary trap that many of us are likely to fall into, and I wouldn't be surprised if I fall into it again in my future. They're just so appealing, aren't they? These off-the-shelf gridded climate products, gridded hydrological products, gridded agricultural products that give you beautiful time series and maps of what's supposed to be going on all over the planet. And the trouble is, of course, that particularly where these are generated at global scales, they're often not very well constrained at the regional or local scale, and that they also are often checked and bias corrected to very specific metrics, which may or may not be the ones that work for you. So I'll illustrate this with some work we were doing over the Amazon basin, where we really wanted to understand what the history of deforestation in this basin was doing to the production of stream flow. So this is something people had tried modelling, but hadn't really been empirically investigated. Now, of course, if you want to know what something like land cover is doing to stream flow, you need to firstly be able to control for the changes in rainfall that is the major driver of stream flow. And this left us with a difficult question around which data product we should use to represent the rainfall over this large area. And broadly, we had two choices. We could try to go for satellite-based or satellite-derived products, or we could try to use the Brazilian government's rain gauge network. Now, we actually thought, starting out, that the satellite products were likely to be superior for our purposes. The Amazon basin, it doesn't contain the Andes Mountains, right? It's relatively flat. It's relatively homogeneous in its land cover. It should be a place where we should make good observations of rainfall, we thought. And on the other hand, this gauging network, even though it looks quite dense, if you look at the very dense dots on that map in panel B, that map is over a really, really large area. And so the average area that each of those rain gauges had to represent was 13,000 square kilometres. So really quite sparse. So our expectation was that satellites would be better, but we really didn't know. So what we did was take several satellite products, but also to take this rain gauge network and do several different kinds of spatial interpolation in order to make some maps, or to pull out some, to make some maps. And what I'm showing you here on the right is an example of those maps for one particular metric, which is the average rain delivered per storm. And for us, this seemed really relevant because, of course, if we're going to analyse stream flow, we're interested in things like peak flows, which are likely to respond to individual storm events. Well, this map is not, well, these series of maps are not very encouraging. Just to give you some context, the first four, so the top row and the left-hand panel in the second row, are data coming from satellites. The remainder are the custom interpolations that we did of the rain gauge network. And the differences in terms of magnitude are, when we look at areas that are bright red, then the mean storm is somewhere around about 5 millimetres per storm, compared to maps in dark blue, where the mean storm-based rainfall is about 4 times larger. So that's quite a difference, a factor of 4 in your description of how the rainfall comes. And of course, it also has implications, for instance, around how often these different products are seeing their rainfall. In fact, if we mapped this not as the storm-based metrics, but in terms of total monthly rainfall, all of this looks much more similar because the satellite products were bias corrected to the monthly rainfall. So if we were doing monthly rainfall, things would be fine, but we're interested in things that happen faster than that. And that means we need to get the storm-based stuff right. And these satellite products just haven't been made to agree with the gauge data on that timescale. So now we're faced with a real problem. We want to do this analysis of stream flow. We've got these really different representations of how the rainfall works coming from these different products. What do we do? And in this case, the answer was not too hard to find. We know that if we want to have a reasonable description of stream flow with our rainfall, that the rainfall should go up and down, and the stream flow should be going up and down in a way that's pretty well correlated with the rainfall. And for example, ideally, there should be a rainfall event before there's a peak in the stream flow, so that we would have this sort of continuity between the way that rainfall should be driving that stream flow process. So we analysed all of these data sets in terms of the correlation between the rainfall and stream flow time series on a per basin level, and also in terms of where the peaks in the 2 time series aligned with each other. Did we see stream flow peaks within a few days of a rainfall peak? And I haven't really shown the formal graphs here. This is really just an indication, but what you should be able to see in each case is that there's a curve given in pink, which is always standing out from the pack, either to the right-hand side on the top of those, in those top panels, or vertically in the bottom ones. And what that's indicating is that this particular data set did the best job out of all the ones we tested. That turns out to be the inverse distance weighting of the original rain gauge network, which again was not what we expected at all. And you'll also notice that if you sort of look to the left several curves in the top rows, or look down several curves, that you'll see a solid orange line. And this actually turns out to be the best of the satellite products in terms of how well it corresponded to stream flow on the ground. Now, I'm certainly not advocating that you take any rainfall product and correlate it with your local stream flow, because, had we been interested not in stream flow, but say in evaporation or soil moisture, it might well be that a different one of these products would perform better. my point here is that not all of these available gridded products are the same, and that they may be better or worse suited for helping you answer questions about your water system. And so that convenience of grabbing the off-the-shelf product is one that needs to be, I think, really critically examined relative to these sorts of challenges and the uncertainty you might be injecting in your analysis by grabbing a data product that's not so well suited for your purposes. Well, my last trap is another one about being uncritical. This is the one where you uncritically believe your model. And, you know, modelling, of course, is a giant can of worms around ways that things can go wrong. You know, your model might just be bad. And if you want to hear me waffle on about bad models, there's a recent talk on the rational method that's available on YouTube. What I thought I'd share with everybody today was sort of more in keeping with our Arcavity discussion, issues that come up when you're modelling changing systems. And, you know, what we saw in the Arcavity was that as the system changed, it seems really likely that the dominant runoff generation mechanism also changed. And sometimes people are calling this a shift in the hydrologic regime from, you know, say one that's dominated by groundwater discharge to one that's dominated by surface water discharge. But we don't even have to get into dramatically changing systems to see that the dominant processes might vary. So, for example, if I just show you these two photographs, I hope you would agree that we might expect different runoff generation mechanisms to be important in the relatively light rainfall shown in the top image as compared to the very intense rainfall shown in the bottom image. So even just looking between different events, we might see switches in which mechanisms matter. Now, if you've got a very mechanistic model that allows for different processes to be triggered by different states in the catchment and features of the climate, this probably isn't a big deal. But for many of the models that we use, of course, we don't have that level of process representation. Very often we run lumped models that have a single process representation for generating runoff and which really deal with things like switching processes through calibration and hoping to get some sort of mean behaviour right. So an example of such a model would be the urban model SWIM. SWIM is really widely used, of course, all around the world for understanding urban systems, and it's invested a lot of its complexity and thinking into representing elements of the urban stormwater system, so the pipes and the grease traps and the compensation basins and all of this sort of stuff. What it hasn't invested its time and energy in quite so much is its actual hydrological model, which is very, very simple at the subcatchment level. So even though individual urban subcatchments are characterised by really complex spatial patterns of impermeable surfaces and permeable surfaces, and that's what this image in the middle is trying to show. This is an urban cul-de-sac where the impervious surfaces are coming out in grey and the permeable ones in green. SWIM can really only represent that with a pretty lumped approach shown on the right-hand side, where we get two different flavours of impermeable surface area and one flavour of permeable surface area, all treated in a lumped way. So specifically, what SWIM does in the subcatchment is to represent all of that spatial complexity with three parameters. One of those is the impervious surface area fraction, and I would argue that this is pretty much a physical parameter. It's certainly an observable parameter that you can observe in satellite images. But then some fraction of that is designated as the directly connected impervious area. And this is intended to also be a physical component of the catchment. It's meant to be this part of the impervious surface area where flows can go directly into a catchment outlet, or in this case, a drain inlet. But in practice, this is often a calibrated parameter. And the other parameter that you can play with is referred to as the catchment width. So all catchments are treated as rectangles. Those rectangles have a width. But again, in practice, this is often a calibrated parameter that people have argued is better thought of as something like the inverse of the mean flow path length in the catchment. So what happens with a model like SWIM as you try to represent complex spatial landscapes that SWIM has to kind of calibrate its spatial properties over, varying climatic properties, and changes in your observable parameters. So say changes in the degree of urbanisation and that impervious surface area fraction. That's what we wanted to investigate. And I guess you can sort of think of two different endpoints. One is that these parameters that we calibrate are fundamental properties of the structure of the catchment, in which case they should not care too much what happens as you change the climate and the fraction of the impervious surface area. At the other extreme, these properties may not really have a physical meaning at all and just act as calibration parameters, in which case we might get some problematic behaviour showing up. So to explore this, we took images of urban catchments and binarised them to say, you're now the impermeable bit, you're now the pervious bit. And we also did that with different thresholds for binarisation so that we generated different versions of the same image with more or less permeable surface area. So this was our attempt at representing, at the one extreme, maybe a peri-urban area that's still mostly undeveloped, all the way through to a almost fully developed area while retaining the same overall spatial patterns. We also, through different rainfall scenarios, so peak rain intensities that varied from the fairly intense 2 centimetres an hour up to a seriously intense 8 centimetres an hour, and different soil properties so that our permeable areas would infiltrate at different rates. What we then did was simulate all of these different combinations of the images, the rain and the soil using a spatially explicit overland flow model, and we predicted the fraction of the incident rainfall in the catchment that was discharged and the fraction that was infiltrated. We then ran the same scenarios with SWIM, varying the width and the directly connected impermeable area as these two calibration parameters. And we did this having checked in a sensitivity analysis that that was a sensible thing to do. And then we looked at how well the SWIM scenarios compared to the spatially explicit model output. And we looked at really the error in the infiltration fraction between them and used this as a calibration metric. So that at the end of all of this, we had a whole bunch of SWIM simulations for different properties, all of which could be related to these spatially explicit model simulations for the same image. What we then did was say, well, let's set a threshold for how close these numbers need to be and say that any set of properties, any set of calibratable properties that meet that threshold gives us a feasible set of parameters. We called these the behavioural model parameters. And then we said, all right, well, now let's do that and let's look at how this space of parameters that work okay starts to change as we change how intense the storm is or as we change how much of the catchment has an impervious surface in it. And what this big old scatter plot here shows is really the change in the shape of those dashed grey outlined areas, which is saying that, look, for the same spatial properties in the catchment, the parameters that give us the right behaviour when we calibrate them do seem to be quite dependent on the storms to which we calibrate them and also the condition of urbanisation under which we calibrate them. Now, why does this matter? Well, if we calibrate our models today, if we're using SWIM, and let's hypothetically say that today has fairly low intensity rainfall and urbanisation hasn't really taken off in this area, but I'm concerned about climate change when I think I'm going to see more extreme storms, and I'm concerned about urbanisation when more of this catchment surface area will be impervious, or both of those things together. We need to now think about how this changes whether our calibration has worked or not, right? So here's our initial conditions. And so I've pulled out the example for where we do have low impervious surface area and fairly low intensity rainfall. And under these conditions, this model barely cares about what parameters you give it, provided that the directly connected area is less than 0.6. Everything in that space behaves itself okay. The model just doesn't care. But okay, that's our little error distribution. So this is showing us that for everything inside that box, the mean error is 3%. So you'd feel pretty happy if your model was correct to within 3%, I think. But now let's say that we greatly increase the impermeable surface area and we go from 10% impermeable surface area to 90% impermeable surface area. that big rectangle shrinks down to these isolated little diamonds. And these are the only parameters that will actually reproduce the runoff responses that we get from our spatial model under these circumstances. And even though the mean error across that big odd rectangle is still fairly low, what we can see is that that error distribution has been stretched right out. So depending on which set of parameters you used, you could be getting things wrong by minus 30% or plus 20%. So our errors greatly increased when we take these historical parameters and apply them to this future land cover scenario. And look, we hit the same problem if we take our historical parameters, keep the land cover the same, but now we make the rainfall much more intense. Again, we get this big stretching out of the errors and this big collapse of the behavioural parameter space. And the same thing again if we have both land cover and climate changing. Now, on the one hand, this seems kind of obvious. It's another version of the past is not a good guide to the future. But we can imagine that in a model like SWIM, where these parameters sound like they're representing physical properties of the catchment that shouldn't be changing, users may not feel very cautious about asking whether these parameters are still good as you test new scenarios. And of course, why do we do modelling in urban areas anyway? Well, a lot of the time it's because we are interested in what will happen if we have more urbanisation or if we have a different climate taking place. So this expansion of error, this great increase in our model uncertainty by applying it to futures that are very different from when it was calibrated is a real problem in SWIM. It's going to be a real problem in many models, particularly those that do rely on lumped parameters to represent effective hydrological behaviour, because that effective behaviour usually is due to interactions with the rain climatology, the land cover, and what else is going on in your catchment. So as those things change, those effective parameters will also change. So this problem's quite big for SWIM. When we looked across a whole range of possible climate and impermeable surface area changes, the sort of errors stretch out to plus or minus 60% in terms of how much rainfall infiltrates, and suggests that we do need to be really cautious about this when we're modelling future scenarios. So those are my 5 ways of making errors. Believe the gurus, ignore the runoff generation mechanisms, use a single method of exploration, trust gridded data products, and believe in your model. We need someone to save us from these traps, right? We need Batman. I don't have Batman for you, but I have some things that I think are really helpful in not falling into these traps. And the first of these is to really remember that our hydrological study areas are real places. And as an analyst, as an investigator, you need to get to know those places. You want your boots out there on the ground, and in particular, get out there when it's raining and see what the hydrology is actually doing. There is no substitute for this. And it can really let you see that you might have some ideas about what's taking place that really fit in well or really don't fit in well with what's going on the ground. So this image, for example, is a tributary to the Arkavati. It's the Kumudavati. And this is at the height of the wet season. And you can see there's not a droplet of water in this channel. So, you know, I see this and I think, well, anyone who's telling me that that river is now a series of lakes is crazy. There's just no water in the channel. That can't be a good explanation. You need to spend time in the places that you're trying to understand to the extent that you possibly can. And as much as you don't want to unquestioningly believe your gurus, you should go talk to them and talk to all the people who might have some ideas about how a place is working. In the worst situation, they'll all disagree with each other, and you'll realise that you have a really important job to do and something to offer. I would say the next thing for hydrologists is really understand the flow paths, and this is something that you'll be able to do if you do go and spend time in the place that you're studying. Why do you want to understand the flow paths? It's going to make the rest of your life so much more effective. It will help you choose models that reasonably represent the sorts of things that are going on in your catchment. It will help you design ways to measure the main fluxes. It will help you identify appropriate control volumes and how you constrain them and how you pull a water balance together. It will really, really give you the insights that are needed to have the easiest pathway through analysing a water system. I think you also need to be really careful with off-the-shelf products, and this is true whether you're looking at models or whether you're looking at data sets. I think I've been a little bit horrified lately with the number of very simple models that have really fancy GIS interfaces and produce these beautiful maps that look so authoritative and wonderful. And then when you look under the hood, you think, oh, that's a lot of precision in that map relative to how much certainty this model really gives you. So check what's under the hood. If you're thinking about data, check that the data product you're using is really well suited to the purpose for what you want to use it for. So that might mean, checking how well it agrees with truth measurements, or it might mean checking how much it varies with other products, but in a way that is related to whatever it is that you need that data product for. And wherever you can, do test whether things are valid in your study area, because sometimes they just really aren't. We recently tried to use some TRIM satellite rainfall products in the Ethiopian highlands, and it was just, I was so glad that we spent the time trying to compare it to ground gauges, because it was really disappointing and there was no way we wanted to be using that satellite product. So even though TRIM's a wonderful product, there are places that it doesn't work very well. That might be your place. Go check it out before you trust it. But the biggest one that I really want to put in front of everybody is the idea of the method of multiple working hypotheses. And so if you go onto Google and you Google the scientific method, you'll probably see a diagram a little bit like the one on the right here, where you make some observations and then you create a hypothesis, then you do an experiment to test the hypothesis, and out of all of this comes your theory about how something works, or your model, or whatever. And that's really nice, but it's altogether too neat. And so I would like to suggest that we replace this very monolithic and linear take on how to understand things with something that is a lot broader. And yes, you should go make your observations, but what I'm hoping is that having made those observations, you're not going to have just one hypothesis about what could be going on, but many. And I think there's a really important part of study design and conceiving of a research project where you dream up as many of these hypotheses as you can, as broadly as you can. And what that can then let you do is conduct multiple experiments that probably don't leave you with only one hypothesis standing. They probably leave you with 2 or 3 or several hypotheses that are still plausible. But now you're much further along in your understanding of the system. You're really confident that you've ruled out those other ones and that you can take things forward in a much more focused way. I think particularly if you're working in places that are changing very rapidly, or that have historically been under-observed so that you're not really drowning in data, that this kind of broad-minded approach is really valuable, because often we don't really know what's going on in those places, and you don't want to fail to hit on the right answer because you failed to include that hypothesis at the beginning. So look, I could give you many more models from my life, like the way that water doesn't cause these patterns, but water totally caused these ones, except for that one that I just put the cross through. This was a big model for us. Or the way that this beautiful straight line, that one down on the bottom left, isn't that lovely? Oh my God, I was so excited when I saw that line, but it's actually a sneaky mathematical artifact that you have to get rid of if you're trying to understand river recessions. I spend a lot of my time being muddled, and I'm ready to embrace this cuddly muddle-headed wombat as my spirit animal, I think, because while hydrological muddles are not good to cause or to put out there in the world, recognizing when you yourself might be a little bit muddled is something that I think is very much a positive thing. Because if you're muddled, it means, and you're prepared to admit it, it means that your ego isn't getting in the way of being truthful about the limits of your knowledge. And that means you can have honest discussions without projecting false confidence, without getting yourself into a situation where people are making decisions based on what you're saying that could be entirely wrong. It's okay to be muddled, and that might just be where you're at, and might be an indication that more work needs to be done before a decision is reached. fundamentally, as a scientist or a researcher, if you're feeling a bit muddled, that's also a good thing because there's so much more to learn, and it means that you're still on that learning pathway, which is a jolly nice place to be. So I'll leave it there. These slides have a bunch of references to the many studies that were referenced there, but hopefully you can grab those afterwards if that's of interest to you. So I'm happy to stop that formal presentation now and take any questions if anyone has them.
Thank you, Dr. Sally, for the lovely presentation on basically what not to do and hopefully try to learn what to do. We are ready to take questions and they can come up. So I've already got one question, which is how to spot errors in someone else's published results when the data that generated these figures is not available publicly. Research students sometimes end up spending so much time reproducing results, which of course is which cannot be reproduced. This is by Denzel. Thank you, Denzel.
Denzel, I wish I had an answer that was relevant to you and your situation directly, because I think it's almost intractable. Where I think the responsibility lies is in the publishing community to demand that reproducible science become our standard. I don't know if anyone's been following the unpleasant case out of the University of Santa Barbara around the researcher who studied social spiders. So it's a very big scandal and retraction of what looks like was probably fraudulent data taking place. And the places where the studies that have been able to be acted on were those in journals that required that the data be provided. And all of the ones that are still pending some decision are in journals that did not demand the data. So I don't have a good answer. I think, there's fraudulent data. People do really dumb things like copy and paste with a transposition. So you can look for patterns in data if you're really thinking about fraud. Errors, if the errors are in the published data, my guess is they're there because they're so subtle that the authors themselves didn't realize they were erroneous. I'm sure we've all experienced that, right, with errors in our own work. The really big ones, you realize there's a problem because your results look silly. And the ones that take a lot longer for you to find are the ones that aren't giving you those silly results, that they're subtle and they hide. So, look, I think the publishers and the journals, we need to push more and more for open data and for reproducible science. At a personal level, I think ideally don't try to reproduce others' results and have more independent work. Everybody I know who's done the activity that you're describing, Denzel, of trying to pick up someone else's model and make it work, or trying to reproduce something that others have done without all of the information, have found it to be a really unrewarding task. Very difficult.
Just to add here, Dr. Sally, there's another similar case going on near Bangalore, like in another institution, where the root cause seems to have been the unrealistic or the expected result that the PI had. The PI already had something in mind, which is kind of that my end result or my hypothesis should be this. And then the data was asked to be fit. And then the results blamed on the student of it. So there might be a lot of pressure on the students to actually produce results which fit a hypothesis that the PI might have in mind. In that sense.
Absolutely. This guy at Santa Barbara was the PI, and it was actually it was postdocs and junior collaborators doing exactly what Denzel's describing, trying to work with his data, who uncovered the problem. The situation you're describing, Manish, is really nasty. Ultimately, my belief is that if you are a PI, to a large extent, not to 100%, but to a large extent, you have responsibility over the ethics and credibility of the people who are working for you, so that if your students completely have pulled the wool over your eyes, okay, you've been fooled, bad luck. But I think PIs have responsibility to be working with their students collaboratively and to be able to have confidence in their students' results. And if a PI is pressuring students into doing bad science, that's the PI's problem. And, to me, those students really sound like victims in a terrible situation. So I'm so sorry to hear that. Sounds awful.
Can we have the next question, please? So the next question is from Priya Shankar. What are the most essential data required in water sector to solve for water security? How to get them?
I think the answer varies a little bit depending on which part of the water sector that you are in and the main water sources. So look, in general, what do you need? You need to understand supply and you need to understand demand. So as a hydrologist, I tend to be more on the supply side of things. If you're working in an area where that supply is mostly surface water, then you really need to understand what are the flows coming, what's the rainfall driving that, and you need to have some process understanding of what's going on in between rain coming in and stream flow coming out. Now, if you're in the groundwater driven area, the same sort of thing, rain coming in, but now recharge coming out and how that's recharging the groundwater. These data are not always well collected. They're not always well available. And I would say that this is going to be a gross generalization, but very often the detailed understanding of what connects the rainfall coming in to the creation of that stream flow or that recharge is often really oversimplified by water managers. And I guess I'm thinking about here in Western Australia, where we have a very pronounced drying trend in our rainfall, and the possibility that as rainfall changes in its timing and how big the storms are and how heavy the rain is, the possibility that that could lead to quite non-linear responses to the rainfall decline. So that stream flow, so rainfall might go down by 10%. The management assumptions usually are that that's the same change that we'll see in the stream flow or in the recharge. But what we often turn out to see is that the rainfall comes down by 10% and the stream flow drops by 50%. Why is that? Well, it's because of all the things going on in the catchment. So very often that, I think, is where scientists can add knowledge that can help with management, and very often where some of the gaps about how to deal with changing systems are. So look, we can certainly get rainfall estimates from a lot of these satellite products. There's rainfall data collected on the ground that can be used to help work out if those satellite products are making sense or not. They're very hard to compare because they're really measuring different things, but you can put them together. I think a big challenge that's been called out in the Indian context around groundwater has been the fact that in many groundwater monitoring systems that the states and the agencies manage, when groundwater wells have dried up, they have been dropped from the monitoring network. So there's a problem with bias towards the places where the groundwater may be higher. So that's another kind of trap that's out there, is thinking very critically about where measurements are being made and whether or not they're representative. I know that has been a problem. But often we are reliant on local management agencies, state agencies, local government to obtain the data that are needed, because usually they are local or regional data, not globally available products.
I somehow can't hear.
Oh dear.
Oh yeah, now I can. So
Okay.
you were silent. I was wondering. I don't think there are questions from the side. I wanted to ask, expanding on this, there are regions in especially like Himalayas where there are actually very little data available, and especially at the resolutions or the scales at which you ask these questions of runoff generation mechanisms and all. So point one is that when you don't have much data, you are relying on, as you mentioned, TRIM, so satellite data sets, satellite or gridded precipitation data sets, some of these. So how much reliable do they become in these scenarios? And second is that the data that is generally available, which is at the river network level, which is kind of something like the government data, which is generally manually collected as well. Then the reliability of that data I really like when you said that you have to go in the ground and see what your system looks like, because I've known MTech graduates basically submitting dissertations on sites where they've never gone, just using this government data.
Yeah, look, it's really common, right? And I presented a bunch of stuff about the Amazon, and have I gone all over the Amazon in a boat? No, I have not. So there's limits to what's practicable to do, and I don't want to be rude about anybody who doesn't have the ability to get to their study sites, just that it's a good thing to do if you can. I think the point around data scarcity is a really, really important one. If you take a map of the parts of the world where we believe water security is the greatest threat, and you overlay that on where we have, say, stream gauging, that's like a jigsaw puzzle. They perfectly don't meet with each other. So where we need the information the most is often where we have it the least. It's a real problem, and it's one that really can only be fixed via investment in gauging and observations. And of course, we also see that globally there is a trend to not invest in that, but to go the other way around. So I think there's a few things to think about. One is that there are different kinds of ways to make analyses and predictions and run with models about different places, and some of those are more or less data hungry. So, for instance, we've done quite a lot of work in the Himalaya in Nepal, looking at where we could use very simple stochastic modelling frameworks to estimate flow duration curves for micro hydropower. And those are very light models, right? They really need information about rainfall, and they need a little bit of calibration to very short gauge records. And then you can start extrapolating them between catchments without it being too bad. So, that's a very different approach than I'm going to take a fully gridded model and try to make great predictions. And it's, you wouldn't want to use it for all purposes, but maybe you can use less data hungry ways of trying to understand your system in places where data is scarce. And I think we need to think a lot about what we can do to kind of broaden our arsenal for having those lighter, less data hungry approaches. When it comes to the satellite products, I think we hit a triple whammy when we get to the mountains. They're hard to gauge physically. They're often very important for water security, and God, satellites work badly over rugged terrain usually. So it's really problematic. But I think the positive thing, so some things are going to be more reliable than others, right? A snow cover metric is going to be pretty reliable. A rainfall metric is probably going to be pretty crummy. But what you can do is take multiple independent satellite observations and see how well they agree with each other. And what we've suggested trying to do is to say, look, in some of these places, for some of our studies, the uncertainty associated with some of our data sets needs to be part of the uncertainty analysis that goes forward. So we're not just going to ask, how good's our model parameter calibration? We're going to ask, how good is this data? And one way you can measure that is to say, well, if I look at TRIM, then I look at CHIRPS, and I look at Persian, and I get my metrics out, and they vary between them, well, maybe I can now build some sort of distribution of the uncertainty from that into comparison. Now, that's pretty labour intensive. It's not something I'm seeing a lot of people do, but you see what we just saw in the Amazon, like 4-fold differences in what you would have said the rain was, just based on where what you chose as your data. So I think it's sort of underappreciated, but probably worth considering if it's really important to get quantities right, I think in particular. Yeah, and look, I think the final thing to think about is what can be done to try to make measurements in new ways. So, we are in the middle of a digital revolution. We are in the middle of a automation and artificial intelligence and robotics type revolution. And okay, right now, who's employing that? Well, here in Western Australia, it's mostly being done by big mining companies who'd much rather have a robot truck than a person driving it. But do these give us ways to get to inhospitable places and to measure the environment in ways that we haven't been able to before? Maybe they do, and I think there's a lot of space for innovation for these difficult environments there. I'm really bad at that myself. I can tell you that some terrible mistakes I've made trying to do that kind of thing. But there are people who are really good at it as opposed to me. It's worth thinking about. And particularly if you're based somewhere like Bangalore, where there's so much innovation and so much technological capability in the air, there's so much scope.
Just an addendum to that, and I think we'll end with that, is key. We, especially with pandemic coming, it has taken probably a year and a half for people who were planning to do the field work, like early PhD students, especially who are working on database topics. I think there might be a higher reliance on for them on some of these resources, which are available free of cost, or there might be a push from the PIs as well, because there's a timeline attached to the whole thing and all that. There's probably no easy answer to this, but if you'd like to comment, what to do and how to go about it.
I mean, there's no easy answer. If there was an easy answer to this pandemic, wouldn't that be better? Look, I think the whole scientific enterprise over the next few years, well, I think what the global scientific enterprise should be doing is taking a bloody long, hard look at itself and saying because people are disproportionately impacted by this pandemic, right? So I'm about as insulated from it as any human being is. We've barely had a case in Perth because our borders are all locked down. So I'm at one end of the spectrum. I can't fathom the suffering that people went through in India. That's another pole on this spectrum. And then even if I look at, say, my female colleagues who are parents in the United States who've been homeschooling their children for 18 months while trying to work, compared to people who aren't parents, their experience scientifically is different again. So I think what we've seen in every field is that this pandemic has blown up the inequalities that were already there. That's going to be true in science. And what I hope is that we can find ways as an international community of researchers to respond to those differentials with grace and with a degree of compassion towards the experiences people have had. Now, I don't really know whether that will happen or not. What we've been trying to do, for instance, at the Journal of Hydrology, is to recognise that there's been a very strongly gendered impact of the pandemic. So I'll just quickly spruik that we've got a special issue for women in hydrology, trying to celebrate female-led and majority female research teams in particular, but also asking people if they have an important female mentor whose hydrology they would like to feature in a review to submit that sort of work. And we are really hoping that, for instance, women from developing nations will take this up because we suspect they've really had the hardest time of just about anybody. That doesn't do a lot for men in developing nations who also are disproportionately impacted relative to men in the West. But I'm hoping that we'll see at least some of these sorts of initiatives to try to level the playing field a little bit, because it's really not been an equal experience of the pandemic at all. But basically it's bad, and hopefully we can respond with compassion and grace.
Yeah, but thank you. On this hopeful note, we'll probably end here. Thank you for giving your time. I'd also like to thank Sai Veena and Rashmi from Atri and Sai Veena from IIT Bombay who helped with the talk. Thank you very much. It was lovely to have you here.
Thanks so much, guys. Best of luck with everything. I'm happy to supply any of these slides if that's helpful, and just best of luck. Hopefully we'll see you all in Australia one day.
Thank you.
Okay, bye.
Bye. I think we've ended.